Okay, so I believe there's a couple of things worth doing today for this review class, depending on who's attending. There's a few of the normal distribution questions that we didn't really get to practice too much, and also a concept within normal distribution actually that relates back to binomial that's worth discussing to further improve our understanding of the normal distribution. So we'll definitely do a bit of that. And then, so long as we have people from Unit 1 and 2, there were also some stuff in the Monday class that we just sort of essentially ran out of time to get to catch us up to the Unit 1 and 2 calendar, or the planners that other people in the class have. So as long as we have Unit 1 and 2 stuff, we'll have a look at that. Yeah.
So, yeah, and we look at continuous probability distribution applications.
Applications.
Did
Yeah.
we do the
Was there
applications?
a thing specifically you saw? Because I mean, maybe it's in a chapter review, chapter 5, but let's have a look. What do they have? Um, do they actually have applications? I mean, it's pretty much always just a function and they give like a bit of a story behind it. It's like, yeah, okay, the probability distribution is of electric components, or like, length of pipes. If we have a look at continuous, for instance, if I pull up my notes, I think we had like a phone call example. Actually, that would have been in statistics, I think. And so, like, one of the things with probability is that it's pretty much all application. Yeah, here we go. Like phone calls and stuff like that. It's pretty much all applications in the sense that they put a story around it. Um, did you want to practice a few of those kinds of questions?
Um, yeah, perhaps.
Yeah, sure. Okay, let's do it. Right to the external response section. The first one that has a bit of a story in there is going to be question 2. Distribution is about the life of certain electrical components. We're given the following function for continuous. What is the value of A? Does anyone remember how we handled this kind of question?
Do we use the solve function, the
Yep.
solve for A,
Solve for A
and
is...
we do the integral of that function from 100 to 1,000
Yep.
since it's zero everywhere else.
hmm
So we do it for 100 to 1,000, and then we set it equal to 1, and we solve for A. A.
Yeah, that's precisely it. So effectively, yeah, when trying to solve for that coefficient, anytime we're trying to solve for a coefficient, we're essentially just going to force the integral over the full domain to be equal to 1, and then, whatever coefficient comes out to achieve that will achieve that. Nice. Next up, probability that a component will last longer than 950 hours. What might we be doing there?
So we find the integral from 950 to 1,000.
Yep, exactly right. 950 to 1000, because it's longer than 950. So yes, that will be our lower bound. 950 to 1000 of our function. And whatever comes out is said decimal places, so I guess we're just going to control enter that. Next up, a statistic this time. Find the expected value. Do we remember how to do expected value of continuous?
It's just the average value function.
Uh, what would that be?
The um, integral of a function from a to b
Oh, okay. So yeah,
over
you
b
mean the
minus a.
yeah, the average value equation. Not quite here. So expected value and average value are separate things. The average value equation is there to give you like the average y value. When talking about like continuous probability, expected value refers to like more specifically like an x, because the outcomes for continuous probability are on the x-axis. So I understand why you probably thought that might be the case. The wording of the equations are quite similar, but different applications. So for expected value, it'll be on your formula sheet as well. You don't actually have to have it memorized. If I pull up the little cheat sheet that we have, expected value, the mean, is just x times f of x, the integral over the full domain that we have. So if we apply that to the question, expected value, it's integrating from 100 to 1000 x times f of x. 100 to 1000 x times function dx, and whatever comes out of that is our expected value. It's just one of those things you'll have an equation for. Part D, find the minimum life for the longest lasting 50% of components. So remember that life expectancy is on our x-axis. We want to find the minimum life such that for the longest lasting 50% of components. What might we be doing?
I don't think I understood the question.
Yeah, that's fine. So if we have a look at trying to define some of the terms, find minimum life for the longest lasting 50% of components. So in other words, minimum life, if we think about what life is actually defined as here, it's life of electronic components in terms of hours, and those are our x values. So this can just be reworded as find the minimum x value for the longest lasting 50% of components. So it's like, okay, cool. 50% of components are going to have some domain on the right hand side, and 50% of components are going to have some domain on the left hand side. Right, the ones on the left will be the least lasting, they'll have the lowest battery life, and the longest lasting would be on the right side, they have the longest battery life. Is that a bit clearer what it's actually asking?
Yep.
Cool. Now that we're a bit clearer on what it's asking, how might we go about solving it?
Do you do the integral from like 100 to x if it equals 0.5 and then solve it for that? Or
Pretty close. It's going to be the other way around. Instead of doing the 100 to x,
Oh,
you'd
yeah.
be doing x to 1000,
Yeah.
because you're looking for the minimum life. But yes, very, very close. So let's do exactly that. Integral x to 1000 function is equal to 0.5 comma x. Oh, actually maybe not x, let's use a, because I'm already kind of using x in the dx there. Can't use a either, that's already defined, let's use b. That's going to give us a plus minus root. If we control enter on that, it should be fairly obvious which of those is the actual valid solution when you look at your domain. If the domain is limited from 100 to 1000, the only one that actually fits within there is going to be the 736. But because it didn't say anything about rounding, at least in this question, technically speaking, you'd have to be giving this the exact answer with the root in there. Though typically what you'll find is in the actual SACA exam, you'll have to round to some number of decimal places. But yeah, that's the approach. If it said like the what would it have to say differently? The approach that you suggested where you have x on the upper bound would be like find the minimum life or find the maximum life for the least lasting components. Yeah, because you're looking for an upper bound such that 50% is below. That would do that. But cool, okay, that's that. Part E, suppose that components are sold in boxes of 50. This will be fun actually. Okay, so these components are now being sold in boxes of 50. The probability of any component in the box lasting less than 950 hours is independent of any other component lasting less than 950 hours. What is the probability that no more that one component, let's rephrase that, no more than one component in the box lasts less than 950 hours. So something interesting has happened here that changes how we have to approach this kind of question. Before I give it away, does anyone have an idea on what major thing has changed? There's a lot more words in there. One of the key skills you're going to have to develop in probability is the ability to recognize when the probability type has changed. Yes, this is in the continuous probability section, chapter 15 review. And it started out with, an f of x, right? As soon as you see an f of x, an a of x, just any old function in a probability section, it's going to be continuous probability. But,
Uh,
were you going to say something?
Yeah, so, wait, no, wait, I thought I knew, wait, thought I understood, but now that I think of it, I don't. Just, wait,
Yeah, no,
please
that's fair.
continue.
That's fair. Okay, so what was I saying? Yeah, so like we knew it was continuous from the start, basically. But when we're looking at part E, because there's so much more background information on this, right? We're now shoving them in boxes of 50. We're starting to see keywords like independent, and we were never really shown, when it came to continuous probability, the function, the use of it was about hours of life. Now it's suddenly asking probability of, any given component in a box lasting less than a certain amount of time. This is where the skill you have to develop is knowing when the probabilities change. This is actually an example now of binomial probability. This is because you now have the setup is whether you last less than 950 hours or more than 950 hours, right? Those are your two outcomes. That makes it binomial. The fact that the probabilities are independent is another criteria for binomial. And the fact that you now have what is effectively a number of trials, sold in boxes of 50, you now have 50 components that you're looking at across the board. These are all evidence that now we have to work things in terms of a binomial approach here. So we have to get our binomial parameters, which is going to be n, p, and x. So let's go ahead and give that a shot. To make things a bit clearer, it can be easier to try and identify what probability we're actually trying to find firstly. So it's asking what is the probability that no more than one component in the box lasts less than 950 hours. So no more than one would mean x equals 0 and x equals 1. So that would mean probability of x being less than or equal to 1. Probability x less than equal to 1. Maybe I should say y actually, because I think x was already taken for the component life cycle. So we'll use a new variable to denote that capital Y is now tracking the physical components themselves. So when it says what's the probability that no more than one component in the box lasts less than that, that would mean you could only have 0 or 1 that lasts less than 950 hours, or in other words, capital Y is less than or equal to 1. Is it clear enough how we've arrived at that statement? Okay, cool. So now we need our binomial parameters for this particular example. We need our n, we need our p, and we already have our x. The x is just like the number of outcomes that you're looking for, in this case labeled as capital Y. N being the number of trials, it's pretty much always going to be like the number of things that you have, right? We already know the probability was in terms of like the number of components. So if it's in terms of number of components, n is going to be how many components globally that you have. So 50 in this case. P is the baseline probability of a success. And we have to be really cautious here with what we define as a success. By setting probability y less than or equal to 1, we're saying that no more than one component in the box lasts less than 950 hours. So our success, oddly enough, is now defined as lasting less than 950 hours. Because the way we've set it up is such that we're talking about components that last less than 950 hours by saying y less than or equal to 1. So we need P, the basic probability of a success, to be whatever the probability of a single component lasting less than 950 hours is. This is where you now have to go back and say, well, okay, how do I find probabilities of things lasting less than 950 hours? That's actually back to continuous. In fact, we could also use our answer for part B to help out with this one here. We already did longer than 950 hours, so if we want to do less than 950 hours, we could just do 1 minus our answer to part B, should we wish. But just for the hell of it, we'll set up another integral, just in case on the actual day of the SAC you miss that. So we want to do less than 950 hours, which means 950 is an upper bound, meaning 100 would be our lower bound. 950 function dx. What are we going to do here? I guess the easiest way to do that would be to leave it as a fraction. And we'll copy that one down. So we got 2, 8, 9 on 3, 2, 4. We have our n, we have our p, we have the probability that we're trying to find. Is it clear enough why doing that integral has given us p, the probability of a success in this scenario? Because this is where these questions get tricky, where you have to use multiple probabilities approaches to actually solve the question. Cool. Okay, so we're trying to solve, using binomial, a inequality, a range of outcomes. So that's going to be a CDF, which apparently I've fat-fingered the wrong buttons here. So binomial CDF, for everyone who wanted to see the shortcut there, it was menu 55B. That gets you right to the binomial CDF. Number of trials we said was 50. Probability of success we said was 289 over 324. If you, for whatever reason, didn't write it down, you can leave that as a placeholder and just like put any old decimal point in there and just fill it in later. It was capital Y less than or equal to 1, which means a lower bound of 0 and an upper bound of 1. And so the probability is significantly low there. There's a probability that no more than one component in the box lasts less than 950 hours. That should be a really, really small value, because lasting less than 950 hours is like right on the border of the maximum life it can be. And so we would expect a really small answer, although giving your answer to 3 decimal places here seems a bit egregious. So let me just double check to make sure I haven't buggered something up there. What's this round to? 0.89. Okay. Did I get my p backwards? Let x be the number of components in a box that lasts less than 950 hours. We found the probability of lasting less than 950 hours by doing that. Did they mean more than 950 hours then, maybe? Because less than 950 hours definitely means 950 is an upper bound. I wonder, because the answers have a different thing. Just to humour it, I'm going to pretend that they meant more than 950 hours. That'll get us the p-value that was written in the answers. And if we go ahead and do the exact same thing using that p-value, we get the number in the answers. Okay. So that is just the book writing things wrong, I think, unless I'm really misreading something there. It definitely says less than 950 hours, which would mean 950 down to 100. I believe when they wrote the answers, they expected the other way around, more than 950 hours. So, yeah, that's what they meant to say. Because if you get an answer like this, and you try to do that to however many decimal places they said, that's not going to go down all that well. Because you're going to just get 0, 0, 0, and that's it. That's e to the minus 46. That's really, really tiny. But okay. Unfortunate wording on that one. But that's what they intended. Clear enough? Clear enough what the issue was there? In either case, the main thing to care about there was, whatever's worded here doesn't really matter so long as you're able to translate that into what the continuous probability equivalent is that you have to calculate, and that's going to give you a p-value. Very common thing to be able to do there. They might even do that with normal distribution as well, actually. They might start out of the question with normal distribution and they'll say, okay, now it's being shoved into boxes of 50 and you're using normal to calculate it rather than continuous. But yeah, that's just a taster of, except for part E, hopefully they're worded better. That's a taster of what the kind of sequence of questions might be like for continuous. Do we want to practice any more of the continuous stuff, or shall we move on to the normal distribution stuff that I didn't show last time? Moving on. Okay, anyone else? I'll move on, and if anyone wants to continue back with it, let me know. Okay, so where were we? Normal distribution. There was one thing that we covered in the actual in the lecture itself, but didn't really actually practice the question, which was, how do you find statistics when it comes to normal distribution? And the way you solve statistics, if those are the things you're looking for, is going to be with this z equation here. Z equals x take mean over standard deviation. It's the only equation, it is the only equation you get in normal distribution, I believe. Unless you're counting the confidence intervals, which is more of an inequality, but whatever. Point being, this is pretty much the only place where the statistics exists, and so it's actually a fairly straightforward question in the sense that you know what equation you've got to use right off rip to solve it. So we saw an example here, which was like, you have the mean, you have a z value, you have an x value, you chuck them all in, and you just solve the other thing. In this case here, it was find mean and standard deviation. So a little bit trickier. You now have to solve for two separate things. Let's see what supporting information we have to help us out. So, it is known that 10% of cats weigh more than 1.8 kilos and 15% of cats weigh less than 1.35 kilos. Those are the two things, two pieces of information that we have. That and the fact that it's normally distributed. So, as always, one of the better approaches for these kinds of questions is to draw up your normal distribution and just sort of get a visual of what's going on. We don't know what the mean is or the standard deviation, so we can't set our middle point of the distribution. But we can use the relative probabilities and the direction that they're pointing to get a rough idea of where to draw these things. Like for instance, 10% of cats weighing more than 1.8 kilos means 1.8 would have to be rather far on this right hand side, because weighing more than that is equivalent to 10%. The other one, oh, did someone come off mute for a question? No, maybe not. Okay, 15% of cats weighing less than 1.35, again 15% being rather small, means you've got 15% on this side because it's less than a certain value, and that certain value was, I just said it, 1.35. So let's put that, I guess, a bit further over, 1.35, and all of this is, we're going to call that 15%. So what we have in equations is probability x greater than 1.8 is equal to 0.1. Probability of x less than 1.35 is equal to 0.15. We have two equations and we have two unknowns. What we want to do is put it into our z equation. X take mean over standard deviation, because if we can fill in the x and the z twice for two separate spots, we can now do a simultaneous to solve for our mean and standard deviation. We have our two x values. We have a 1.8, we have a 1.35. What we don't have is any z. How do we get there? Well, as a reminder, z is referring to the standard normal distribution. The whole idea there is that it's just a very specific normal distribution that has a mean of 0 and a standard deviation of 1. Very helpful, because basically the amount of information you need to work with the standard normal to get z is basically next to nothing, because two of those variables that you need are already filled in for you. Mean is 0, standard deviation is 1. So, how can we use our CAS to get z values? We have the normal PDF, normal CDF, and the inverse normal. As before with binomial, PDF and CDF are used for calculating probabilities. We don't want to calculate probabilities, we already have them. What we want are x or z values. That's where the inverse comes in. The area is the net probability that is pointing left of your value. Mean and standard deviation already default filled out for us. So, if I want to get the equivalent z of, let's say, this spot here, I want to know what's the probability left of that value, what's the mean, and what's the standard deviation. Again, we already know those are going to be 0 and 1 for the standard normal, and we're already seeing on our graph that the probability is 15%. 15%. So for our area, we're just going to put 0.15 thus getting our equivalent z, which I always overestimate this. That's one standard deviation left. I should really draw these graphs a bit more close together. By the way, if you guys are using the Casio, you can actually choose whether it points left or right. For the TI Inspire, you have to always be pointing left. And what I mean by that is like the probability that you write, the area that you write, has to be left of the value you're evaluating. So for instance, if we're doing 1.8 here, I'm not putting in 0.1 as the area, I'm putting 0.9 as the area. Because again, using the symmetry, the fact that everything has to be equal to 1, if 0.1 is to the right, 0.9 would be to the left. So I'm doing literally the exact same thing, but replacing that 15% with 90%. These are my two z values. I have two z's, I have two x's. I can now simultaneously solve two equations. Let's just use x and y. First one, let's use the first z, and that was with x equals 1.35. So let's do that. Let's use x as the mean, and let's use y as the standard deviation. Same thing over here. And that one was 1.8 for the x. X for mean, y for standard deviation. And what comes out is going to be our mean and standard deviation. Do a bit of a quick sanity check here. Right? Like if I have a mean of 1.55, that means that this center should be 1.55. Seems about right. 1.35 is smaller, 1.8 is bigger. I also knew that based on my z values, these are more or less plus minus one standard deviation away from each other. So my standard deviation of 0.19 should make some sense if I add and subtract that from my mean. So if I do 1.55 plus 0.19, I should be pretty close to 1.8, which I am. Obviously there's a lot of rounding that's going on there. And if I do 1.55 minus 0.19, I should be pretty close to 1.35, which again I am. So these are some things you can do to sanity check if you wish, or if you've done it a lot of times, you can just, yeah, take it for granted. Definitely, I guess the only thing you'd really want to check is the mean. As long as the mean's in a good spot, you can be reasonably certain your standard deviation's fine as well. The mean's really easy to check, so it doesn't take that much time. Any questions on how we solve that kind of thing? Whenever you're solving statistics, mean, standard deviation, z or x, it's always going to be your starting point is this z equation here. Cool. That's the main one from there. Let me just have a quick browse and see if there's anything else crazy. This looks like it might be crazy. Okay, we got two separate distributions. Oh god, yeah, that is going to be crazy. Okay, let's have a look. Type A cell, normally distributed, mean of 10, standard deviation of 1. Before we go any further, maybe let's get some drawings. Okay, so this one's labeled type A. Normal distribution. It has, what did I say, mean of 10, standard deviation of 1. 10, which means you'd have like 11 here, 9 here, so on and so forth. Type B has a mean of 14, standard deviation of 2. Type B. What did I just say? Mean of 14, standard deviation of 2. 14. Let's go 16. Let's go 12. In fact, I'll even put standard deviation 2, standard deviation 1. To determine whether a cell is type A or type B, the amount of chemical in the cell is measured, where the chemical is on the x-axis. The cell is classified as type A if the amount is less than some value C, and is type B otherwise. So part A forces C to be equal to 12. So basically, if you measure and get less than or equal to 12, it's considered as type A. So our value of 12 is going to matter on both of these. Let's get these little highlight. If C equals 12, calculate the probability that a type A cell will be misclassified, and the probability that a type B cell will be misclassified. So to be misclassified, essentially it means that you have a type A cell and it was actually type B, or you had a type B cell and it was actually type A. So the probability of misclassification is basically going to be looking at the other distribution and looking at the probability of it being that. So for instance, probability of type A being, actually let me think about that. Probability of type A being misclassified, yeah, would be purely dependent on the probability of it actually being a type B. So if 12 is our magic number, and it is got to be either less than or equal to 12, is that what it said? Yeah, less than our specified value of C, then we will calculate misclassification of A based on the probability of B being less than or equal to 12. So let's go ahead and do that. Yeah, C. So in this case, it's less than 12, which means our lower bound is going to be minus infinity. Yes, in the real world, technically, there's a limit of 0 here, but using a normal approximation, we have to behave as if we have to conform to the normal distribution rules. The mean of B was 14, the standard deviation of it was 2. So there's a 15% chance of B, a type B cell, having, what was it, chemical of 12 or less, whatever that is. And so that means that the chance of being misclassified for cell A should be this. Other way around is now true for type B cell being misclassified. Now remember, C less than or equal to 12 is determining it as a type A. So to be determined as type B means you want to be above or equal to 12. Technically not equal, but you get the idea. So when looking for part B, or type B misclassification, we are now looking at the A distribution and trying to be above or equal to 12 and finding that probability. So 12 is now our lower bound, infinity is now our upper bound. The mean of that one was 10. The standard deviation of that one was 1. So that one has a much less likelihood of happening. Fair enough. Definitely a tougher question to get your head around. It's going to get even tougher when part B says, I'm not going to give you a value of C. I want you to figure out what value of C forces the two probabilities of misclassification to be equal. So off rip, we can say that 12 is not the number, because that gets you 15% on one of them and 2% on the other. So rather than being using 12, what we want to now say is as follows. A is always looking right of a certain value. B is always looking left of a certain value. We want the probability of A greater than some value C to be equal to the probability of B less than C. That's what we're trying to do. We want to make sure that this area left here is the same as this area right. How are we going to achieve that? What do we have to play with? The only thing we have to play with is C itself, which is an X value. Okay. We have some standard deviation values, we have some mean values. I'm not entirely sure how we're going. Oh, yeah, question?
And the probability of A greater than C be equal to probability of B less than or equal to C?
Yeah,
Because
so because it's continuous, the inequalities that you use is a bit whatever. But yeah, I think what's it exactly got to be? So it's classified as type A if it's specifically less than. So, oh geez, what will this be then? What way do the inequalities technically have to be? So this one would be, it would actually technically be the other way around, because to be classified as type A, you have to be left like less than on this side, which means if we're looking right, then it would be greater than or equal to, which would make this one less than. Yeah, I don't really know exactly what way the inequalities would go there. I think it would be the other way around. Point being, it's not actually super relevant for the question because of the way continuous works. But it is a good question. I actually just don't have an answer, really, for that. But okay. As for solving this question, I don't really know what I'm going to do, but just a hunch, I have a suspicion that the Z equation is going to play a role. Reason why is because we have two sets of means, two sets of standard deviations. Our X value is going to be replaced with C, and can we get Z? Well, we don't need it because we got two sets of means, two sets of standard deviations. That should be enough to simultaneously solve for both X and Z. Isn't that good enough? Maybe. What would it look like then? So we'd have Z equals X minus, so the mean of 1 is 10. Standard deviation of it was 1. And then, so that's equation 1. And we have Z equals X minus the mean of 14 divided by the standard deviation of 2. I mean, let's just simultaneously solve and see what happens. We're definitely going to get an X and Z pair from that, because it's two equations, two unknowns. And I'll be very curious to see if that forces those probabilities to be equal. Oh, PC crashed. Yeah, I think you might have crashed in the middle of the explanation. Basically, I was saying I don't actually really know the answer as to what inequalities you should be using there. More so, but the more relevant thing is that the inequalities that you do choose don't really matter for continuous, because it's that whole thing we discussed earlier, which was like the next value after 14 is not 15, it's 14.0000, and then eventually a 1 somewhere. So the way you treat it is effectively the same. And then after that, what we were doing was more of an exploration, actually. I don't really know exactly how I'm going to solve this, but just the hunch based on the abundance of information that we had, a Z equation is a good place to start because we had 2 copies of means, we had 2 copies of standard deviations. So the fact that we can set up 2 equations with 2 unknowns, where Z and X are those unknowns, I have a suspicion that whatever the X is going to come out to be will be our C, but we'll obviously stress test that to make sure it actually works. So let's go ahead and actually we'll just set up another one. That's got a bit too much in the way. -3, 7, 1, 2 equations, X and Y. Let's actually use X and Z because that's exactly the variables we were actually looking for. From there, our 2 equations were Z equals X minus 10 divided by 1, but whatever. And we had Z equals X minus 14 over 2. X equals 6, Z equals minus 4. So the fact that X equals 6, to me, gives me a sneaking suspicion that our C is going to be 6. Is that going to make sense? So a 6 would be very far over here, which would put our part B answer a lot smaller. And a 6 would be... yeah, no, there's no way. Because that puts an insane number. Okay. That's not gonna work. Cool. Alright, I don't actually know the answer to this one, so let me take a peek at the answer sheet and see if I can help us out here. Okay, so this is 16D. Final question. Okay, they did a very similar thing. Okay. Let me pull up a new screen share so you guys can see what I'm looking at. This is the solution doc here. And what they've done is started out the same way, which was making the probabilities equal each other. Probability of X being less than C equals probability of Y being greater than C. They've used Y for type 1. Hang on. X for type A and Y for the amount of chemical. X is the amount of chemical in a type A cell. Y is the amount of chemical in a type 1 cell. A type 1 cell? God, these would be so much better if they actually worded things properly. There's no such thing as a type 1 cell in this question, so I guess we're just going to have to pretend that they meant type B here, because that's the thing that actually had a mean of 14 and a standard deviation of 2. So let's pretend that says type B. Which is that the way I set it up properly? So Y being greater than C means they meant for B to be the one that has the greater than. Okay, so maybe I have my inequalities back to front then. Okay, so that's one problem. Did I have my misclassifications backwards then? Doesn't look like it because those are the right probabilities right there, 15% and 0.02. So why have they got it backwards? Maybe I'm reading this bit wrong. Anyway. What have we got here? So this is X minus 10 over 1. That's going to be the thing that has the mean of 10, standard deviation of 1, and it's got to be less than that. Okay, that's pretty weird. I might have to get back to you on this. Maybe I'll read the end just to see what's going on here. Since the graphs are symmetrical about the y-axis, a number c minus 10 and c minus 14 on 2 are equidistant from the original. Oh, yeah. Because what they're saying there is, if you look back at the drawings that we were doing, was basically because the probabilities are the same and normal distributions are symmetrical, whatever you have on the right hand side will be essentially mirrored on the left hand side to make the probabilities the same. Easiest way to repicture that would be if you imagine the mean at the very center of 10, you have 50% left, 50% right. If you do one step forward and one step backwards, you have some percent forward, some percent back. Both of those are the same because you're equidistant from there. And so what they've done is still set up the exact same equations that I did, which was the x, or I guess c, take 10 equals z, and the c take 14 on 2. What they've said is these z's are now... They've made the z's equivalent. That's weird. I don't really know how the z's can be equivalent because they should be on opposite sides of each other. One should be over here, one should be over there.
Doesn't the z become a negative? That's why. It's a negative c minus 10.
Yeah, that's a good observation. They've chucked a negative on there. Oh yeah, no, that's exactly what it is.
That's a standard deviation on the other side of the...
Yeah, no, perfect. That's actually perfect because yeah, we have the equidistant. It's like positive z on the right, negative z on the left, and so they basically just said, hey, I'm gonna slap a negative on this one, thus putting a negative here. Yeah. But yeah, and then negative z equals, yeah, the negative of that z is the positive of this z, and so they can now be equated to each other. That's fancy. Yeah, good observation. Jeez. And well, we can already see the working out from that point onwards if we look at the screen share. So what does that actually get us? What's 34 and 3 as a decimal? 34 on 3 gets us 11.33. So if we have a look at our picture, does that make sense? So 11.33 would be roughly here. Yeah, that's plausible. Going right of there, left of there. Because the standard deviations are different, this distribution should be a lot flatter than that one, so I guess it's plausible. And you can obviously stress test it by evaluating the probabilities based on that decimal or that fraction. Yeah, good observation. Okay. So the hunch for the starting point was more or less right. Then going from there using the symmetry of the normal distribution, and rather than simultaneously solving these, because these are actually different z's, that was my issue. This is technically z1 and this is z2. This is x1, this is x2. We've actually got 4 variables in there. Simultaneously solving should never have worked. And so yeah, trying to get one z in terms of the other by flipping it from one side to the other was the way to go there. Nice. I'm glad we could collaborate on eventually getting there. Sweet. So these are the kinds of questions that they might chuck at you. Usually the SAC will have at least 1 or 2 of these. An exam might have, it will definitely have at least one, but not necessarily in probability. It'll be like something across the entire board of, well, of the entire syllabus, where they'll put in a separator question, they'll call them. But cool, okay. this gives us just enough time to introduce one other topic that I neglected to mention when we covered this the first time, which was this idea of the normal approximation to the binomial distribution. The only thing you really got to get your head around here is the concept. The questions themselves are pretty chill. The idea that we're going for here is that if you look at binomial distributions that have significantly large n.
Excuse me.
Yeah, question?
You're still on the axes.
Oh, yes, very good. Thank you. Thank you so much. Okay, that's flipped over now. Awesome. Thanks for that. So, as you can now see, as you have a significantly larger and larger n, what you'll see is that the binomial distributions that are created from that, if you look at all the ways in which the probabilities are weighted, looks significantly closer and closer to a normal distribution. And so the idea behind this is basically, if your n is large enough, you can actually just use the normal distribution to approximate the binomial distribution. Why would you do that? I don't really know. Your CAS seems perfectly capable of just immediately solving using either approach. So if it's binomial, you probably should just use binomial. But they will force you to do it in the question. Find an approximate probability, or they'll say use a normal approximation. Where are they going to say? Come on. Okay, I guess the wordings in these won't use use a normal approximation. I'm pretty sure the exam uses that wording, use a normal approximation to the binomial distribution. What it essentially means is for the normal distribution, you need a mean and a standard deviation to calculate probabilities. What they're saying is use the binomial way of calculating mean and standard deviation and shove those into your normal distribution. So if you have a sample of 1,000 people, that is considered a sufficiently large n. 30% of people are in favor or not in favor, so that's your binomial, right? You got an n, you got a p. Find the approximate probability that between 270 and 330. Because it says keyword approximate probability, you're not just going to use a CDF from 270 to 330, where n is 1,000 and p is 30%, even though you absolutely could. In fact, they show you what that looks like here. The fact that they're saying approximate means use a normal distribution way of going about it, which means calculate the mean using those binomial parameters, calculate your standard deviation using those binomial parameters. They've got a really weird actual equation in terms of z there for some reason. You can just use the normal distribution regularly. So we have a look at the CAS, normal CDF, lower bound was 270, upper bound was 330. The mean as calculated was 300, standard deviation as calculated was the square root of 210. Is that everything? Yep, cool. That should come out to be 0.9616, which it does, yes. So I don't really know why they went out of their way to convert them to Zs. It's just not necessary. But yeah. Also, fun fact, a lot of the time in an exam, they actually say, do not use a normal approximation to the binomial distribution for this question. They'll do that because they like using large n, and they don't want you to accidentally use this. So it'll be very obvious whether you're supposed to use this thing or not. It'll say do use it or don't use it. Maybe I can find an example. We've hit time, so if you guys got to go somewhere, then that's fair. But I'm going to see if I can I'm going to pull up at least one or two past exams and see if I can spot that wording.
Thanks, Chris.
Yeah, no worries. Take care.
Thank you.
All good.
No, it's a little bit.
Yeah, you too.
I have to.
Yeah, no worries. Approximate. Can I do this? Does this search for anything? Okay, so it literally just doesn't do anything. Let me manually scan then. It's Probably more likely in an extended response, actually. Where's probability? Here's probability. There you go. Do not use a normal approximation. Or they'll say, use a normal approximation. So that's what you can expect in the real thing. Cool. Any further questions? Happy to stick around for a little bit. Otherwise, thanks for coming.
Thank you.
Thank you.
No worries.